Hello and welcome to the seventh in a series of presentations on system requirements analysis. This one was delivered first in 2004. It builds on some of the concepts outlined in the first presentation on anomaly handling, that is about integrating failure modes and effects analysis with the system requirements analysis. This is the outline. I'll talk about the role and timing of the system requirements analysis and similarly the failure modes and effects analysis. And if failure modes and effects analysis is not something you're familiar with, I urge you to continue on. This may be beneficial in terms of your requirements development in understanding how we can actually integrate into the requirements development what we learned from failure modes and effects analysis. We'll talk about the problem of schedule really misalignment of these two analyses, how they are traditionally done, and talk about how we can overcome that with what I call a design-less FMEA, failure modes and effects analysis, and how we design for failure, and what that ultimately means for methodology and schedule integration and improving our system requirements analysis to handle things that fail. So what is the system requirements analysis? Well, from the INCOSE Handbook version 2, is to assist the customers in refining their requirements in concert with defining functional and performance requirements for the system primary lifecycle functions. So we decompose and allocate requirements to the next lower level of the system design and establish the feasibility of the requirements and the system design, that is the architecture, and define the verification methods and approaches. That's what we do with the system requirements analysis. And this continues up through preliminary design, because preliminary design is when we should have all the requirements completed down to the lowest level components for which we're going to write requirements. The failure modes and effects analysis, and these benefits are cited from the ARP 5580 aerospace recommended practice from SAE in the United States, that's standard, on failure modes and effects analysis in aerospace. The benefits are to enhance the system safety by uncovering failure modes that result in hazardous conditions, assess the mission-related effects of critical and undetected failures, influence the design, mitigate the impact of failures, and support verification, assure that fault detection and fault isolation is designed in the system, assist the design engineer to select a design that will help the operations, and provide data. Usually these are performed during the design phase, but you can infer from these benefits that to have the most impact, many of these items need to be included in requirements, like fault detection and fault isolation, like understanding mission-related effects. So, or understanding failure modes that lead to hazardous conditions. You might want something in the system requirements that address those issues. But if you don't know about them until you've completed the requirements and you're in the design phase, then you're going to have to rework the requirements. So graphically, if we overlay these activities on the systems engineering V, then what we see is that the SRA typically applies from whenever we begin up through the preliminary design review. And when we have a preliminary design, traditionally that's when we do the failure modes and effects analysis. And there's almost no overlap, so that anything we discover in the failure modes and effects analysis for which we want to force requirements, that is motivate a design, and be sure that the system actually implements it, then we're now into rework. So the question is, how can we address failure modes and effects analysis before we finish the requirements if our failure modes and effects analysis is dependent on the design? Well, the answer is we have to do a failure modes and effects analysis without a design. And this is the thrust of the ARP 5580, that we can do what's called functional failure analysis, so that we don't need a physical design. We don't need to know what the solution is in order to perform a failure analysis, because we can talk about failures of functions. What happens if a function isn't performed? Or what happens if the function has degraded performance? Like instead of getting to 60 miles an hour, we only get to 50 miles an hour or whatever. Or what happens if it's the wrong state? It's supposed to output a 1 and it outputs a 0. Or what if it's performed at the wrong time? Like it happens early, or it happens in the wrong mode. And our combinations of all these. We can ask these questions about functions regardless of their eventual implementation. And this is what's key to being able to perform the failure modes and effects analysis immediately upon system conception. You know, I have this concept for how the system is going to operate. And these two pieces of equipment are communicate. Well, what happens if they lose communication, for example? Pretty obvious one right off the bat, loss of function. Well, that means some things are operating in isolation. So what do we want the system to do? Well, that will have to be determined as part of the analysis, but asking the question arises during the functional analysis. We're trying to get all the requirements in the system requirements analysis, and we don't need to know whether it's a different kind of radio or something else. All we need to know is we've lost the function of being able to send and receive. And then we can make a response to that. These ideas build on what I first described in SRA1 in 1995, that every function must have at least one complementary response based on a failure to experience the expected condition. We don't get an input. Now what do we want to do? Because we're expecting an input that was going to trigger a certain function, but we didn't get it. So now what do we want to do? And the detailed list, I mean, we can decompose handle anomalies into many different failure conditions or different ways of not receiving the expected condition, like not at all, wrong value, wrong timing. All those things can lead to different functions to handle those. But the point is of asking the question and realizing that I haven't covered everything that might happen in a real system because things go wrong. Murphy's Law. So every function has to have at least one complementary response that is the antecedent complement to the go path condition that I talked about in the 95 paper. Once we do that, we notice that this is based on functional failure. I didn't get the prior function, so now what do I want to do? I want to do something different, perhaps. It's easy to see this in example, the Farm Road traffic light system after Terry Bayhill's design methods comparison project from 1999. Functional flow is pretty simple for a farmer trying to cross a busy highway with a traffic light. If there's no failures, everything works like it's supposed to. Traffic light system senses that the farmer is there, tells the highway traffic to stop, tells the cross traffic to go, senses that the cross traffic is completed or it times out the lights, then returns the system back to its default condition of the highway traffic gets to go and the cross traffic is stopped. If we start asking, well, what happens under condition of certain failures? For example, if there's no power, well, that one's pretty obvious that all the lights would probably be off unless of course, some enterprising designer decided to put in a battery to allow all the lights to stay on, but for example, turned them all green because there was no requirement controlling that condition. And you might say, well, that's silly. No one would ever do that. Perhaps, but they might, and there would be nothing to prevent them from doing that. In other words, when we fail to define responses for explicit conditions in the requirements, the implementers are totally free to implement whatever they choose for those conditions because it's not covered in the requirements. This is an example of incompleteness. A more common situation might be we get the wrong state of the output. So failing to indicate that the highway traffic is to stop with a red light, or maybe the light goes blank. Well, then what do we do? Well, under normal conditions, then we indicate cross traffic go. But if the highway traffic hasn't stopped, we ought not to indicate that the cross traffic is allowed to go, because that would be dangerous. So we might have a common failure condition when anything goes wrong while powered, flash the highway traffic yellow and the cross traffic red. That converts the highway traffic into a caution and the cross traffic into a stop sign equivalent. But then they could go on if the conditions permit. The point is to always have defined a response for any possible condition, and it really is done at the function level. And each of these functions will yield a requirement. And if it's a response under several different conditions, then the antecedents for those behaviors might be a long list. But the point is, we have a complete set of requirements with respect to conditions. And now there's no, if you will, freedom for the implementer to choose how they want to implement it, because the requirements tell them exactly what the functionality has to be. So the requirements are more complete, and we don't leave the response to failure conditions up to the implementation. It continues to be up to the system architect, the designer, the one developing the requirements, the response to conditions. You can represent this kind of behavior in UML activity diagrams, now SysML activity diagrams. It's the same behavior, just a different notation. So if you want to represent it using SysML, you can do that. But we represent these failure conditions as branches and assign behaviors then for the system of interest. But different inputs can lead to different activities based on what the condition is. So those trigger certain behaviors by the various actors, and the system response is always defined even under failure conditions. So regardless of the methodology, the diagrammatic methodology you want to use, we can define system behavior under failure off nominal conditions using our standard system engineering tools. So what does this mean for the schedule? Well, that means we can move our analysis of failure modes and effects up, because now we're only analyzing functional failure. So as we derive functions early on in the system, we can ask the question, well, what happens if that function's not performed according to one of the functional failure modes, like not performed at all, not performed with the right state, performed with degraded performance, or performed at the wrong time? For each of those, we can ask the question, what's the appropriate system response that we want to document in the requirements? So that the things we learn in the failure modes and effects analysis, we define the appropriate responses in the requirements, and we can verify that the design actually implements that. And we may find out, for example, that we need changes in the system architecture for redundancy, to reduce the likelihood of a certain loss of function, or we want to add fault detection, fault isolation to be able to report on a certain thing to the operator or to the maintainer about our particular failure. But having done this analysis early before the design of the requirements are complete, we have the ability to define these new requirements without disrupting the design activity so much. Eventually, of course, all these new functions will lead to a revised design, but that's the point of requirements. They drive the design. So by doing the failure modes and effects analysis earlier on functional failures, we can develop responses to failure early enough to get those responses defined in the requirements activity before preliminary design review, and therefore it won't be as disruptive of the design activity. So in summary, both of these activities contribute to the system definition. If we can perform the failure modes and effects analysis concurrently with the system requirements analysis, then we're going to have less rework. But we have to be asking the questions about, well, what if certain failures are experienced? What do we want to do under certain off-nominal conditions? Because it may be that some of those functional failures are going to drive design changes because of specific requirements that we need to add. This gets back to what I was talking about in the completeness presentations of validating the responses with the stakeholders. The analyst is going to do the best job they understand from their position about what the system response should be, but that needs to be validated with the stakeholders for conditions that weren't explicit in the mission statements and parent requirements and so forth. So this is why requirements completeness depends on doing this sort of analysis to cover all the possible input conditions and output conditions, and failures of a system to perform properly results in a different output condition, perhaps, to make sure that we actually have everything covered, including the off-nominal or failure conditions. And we don't have to wait for a design to be able to analyze failure, because we can analyze failures of functions and get those responses, appropriate responses, defined in the requirements before completing the requirements and completing the design. So this allows us to have a more complete set of requirements, and we can move into the design phase with more confidence that we've covered everything that we believe is important based on analyzing all the possible conditions, including functional failure. And so I thank you for your attention, and I look forward to seeing you at the next presentation.